Okay, so welcome to Quantum Mechanics 1. So for most of you, this is the first time that you're going to get officially introduced to quantum mechanics, and I'm very, very excited to be the one doing that job. Quantum mechanics is perhaps my favorite subject within physics. And I find it an amazingly interesting and exciting topic to discuss, and I hope I can convey some of that excitement to you. So this class, you can interrupt me anytime. You can ask me any question. I am not the world expert on quantum mechanics, so some of your questions I may not have the answer to. If that is the case, I will tell you, and I will. What I will try to do is that I will look it up or think about it and come back to you in the next class. And so I want it to be a very participatory class. I don't want to leave anyone behind. That is my general philosophy. So if you think that you are not able to cope with the class, please ping me and I will try to help you outside class. And if you have any questions, academic or non-academic, please feel free to reach out, okay? So, now before I, get into the quantum mechanics stuff, I want to talk about some grade distribution as well as some class policies, okay? So this is going to be probably the last of our offline semester, and or not, I don't really care one way or the other. So, it'll be mostly taught on bucks. So the grade distribution is going to be something like this. So there will be 10% participation quiz, okay? So what is participation quiz? So what you will find is that when I post the lectures, and the lectures will be essentially recorded and slightly edited version of the live classes. Once I post the lecture will be divided up into 4 to 6 or 7 pieces, and they will be interspersed with some quiz, which will ensure that you have watched the lecture. The quizzes won't be very deep. So this will be kind of low ball questions just to ensure that you have watched the lecture. So if you attend the class, there is actually, unless you want to, there is no reason to watch the lecture again. You can just go ahead and do the quiz. I don't care about whether you have watched the lecture or not, as long as you have been able to do the quiz properly. However, I would encourage you, if you missed the lecture, to actually go and watch the lecture carefully, because your exam and your assignment as well as tutorials will draw from what we're taught in the lecture, okay? So the participation quiz will be very easy. If you just follow along, you should be able to get 95+% in the participation quiz, okay? Okay, and then what I do is I actually have an attendance policy. So you must attend at least 75% of the class. If you do, then you get 5%. So attendance must be, somebody wants to enter the class. Let me allow them. Okay. So attendance must be equal to or greater than 75%. So it's not like, you get your, proportion of 5% depending on how many classes you've attended. No, either you get the whole 5% or you get 0. So suppose you get 74% of your attendance, you may make a case with me and I might allow you. But if you suppose, you attended 70% of the class, then you will get 0% of this 5%. But if you attend 75%, you get the total 5%. So it's an easy 5 points. And the rationale for having this attendance policy is so that you are encouraged to come to class. Sometimes because might have internet issues, or you might have some stuff going on, unexpected stuff, you may not be able to join the class. And I think 75% is a good enough attendance policy that it'll allow you to not be affected from such unforeseen circumstances. If something does happen, please reach out to me. For example, a few semesters ago, one of my students, he was based in a village which had very bad internet connection, and he had to travel somewhere else to watch the lectures. And I gave him waiver, so he just watched the lectures on his own. So if you think you're one of those cases, please, contact me, okay? So that's 15% of the grade taken care of. So I'm going to introduce what is known as the tutorials. And the tutorials are going to be ungraded, but you must attend the tutorial. So you must have 80% tutorial attendance to pass. If you have less than 80%, you will be failed in this course, okay? A lot of the learning that you will do in this course will be in tutorials. So those of you who have taken my previous courses, you know the format of the tutorial. What I do is that I get somebody, usually a junior lecturer, if I don't get that, maybe an advanced student, who will guide you through a pre-written problem, multi-part problem, and you will solve that problem in a group, helping each other, okay? So physics is a social enterprise. It's a collaborative thing. Physics is highly competitive, but the competition usually comes between groups, Group A and Group B, when it comes to research. But when Group A is working, they collaborate, without reservation. So I hope that in the tutorial, you will learn how to collaborate and you will learn physics from each other through peer interaction, okay? So when you're in the tutorial, don't be stingy, help your friend. Okay, now, number 4 is that there will be 4 to 5 graded quizzes, okay? So 5 possibly, and the graded quizzes will carry 15%, okay? So the graded quizzes are also very, they will be a little bit harder than the participation quizzes, but they will still be not very difficult if you pay attention, okay? And how many graded quizzes? There will be 5 graded quizzes. And in this class, there will be no best of policy, okay? There will be no best 4 of 5 or best 3 of 4, this sort of policy, okay? So there will be 5, to help you, I might do 6 graded quizzes, but usually it turns out that we don't get time. Okay, number 5 is this will be an assignment-based course. So you will get your 30% of the grades divided into 4 to 5 assignments, okay? Now the assignment has very strict policy. And the assignment policy is that you may collaborate. You may collaborate on the assignments, okay? But when writing up, you must not copy each other. And I cannot put enough emphasis on that. You must not, okay? If I find, you know, evidence of copying, I will not call you in for questioning. I will report you to the proctor's office. And the proctor's office usually will disqualify you, will give you an F, and you will lose your scholarship, okay? It is, as much as I don't want that to happen, I just don't have the bandwidth to deal with people who are copying from each other, okay? So this is, I know that BRAC has a very strong culture of cheating, unfortunately, and I want to discourage that. So this is my policy, okay? So is that clear with everyone?
Yes, sir.
Okay. Yes.
You may, you may ask each other, oh, can you help me understand this? And, when I was an undergraduate, I used to, discuss physics with lots of my friends. We used to, we used to discuss homework problems. We used to discuss all kinds of issues, subject matter, but we never copied each other. So you must, write your own solutions, okay? It is very easy for me to, to detect cheating.
I have a question about this.
Yes.
When I help people, sometimes I tell them kind of the algorithm that I use to compute something. Is that considered telling someone how you directly did something? Like I calculated this, then that, then that.
No, I think that's fine. I mean, you should try to, guide them towards that algorithm rather than telling them that, because because we are actually not very, as human beings, we are not actually very good at algorithmic thinking.
Yeah.
I think we are, because memorizing an algorithm without understanding it is just very, very difficult thing to do, in my opinion. So, it's better to actually, it's easier to understand something, right? Then the algorithm just comes out naturally, And
Yeah,
a lot of
totally
times,
understand.
a lot of times, if the problem is interesting enough, unfortunately at undergraduate level, it's not possible to have that many interesting problems. But if the problem is interesting enough, you can do it in more than one ways. So, at least superficially. So, algorithms may or may not be helpful, okay? Okay, all right, so any more questions on the assignments? Okay, the other thing I'm going to do is that I actually provide help on the assignments. I will actually, after posting the assignment, after about a week or so, I will actually have a special class where I will go through and discuss the individual problems. So there is really no excuse for you not to do the assignments. And what I've seen is that a lot of you will not do the assignments on time, even though the number of assignments is very doable. It's 4 to 5, So I will encourage you. I don't, it's in your own interest to get the assignments in on time. If you're late, I'm not very strict about that I don't dock marks or anything. But it's, the more you like postpone the assignment, the less you are engaged with the course, okay? So for your own sake, I'm going to treat you like adults. So for your own sake, I highly encourage you to do the assignment on time, okay? And also because I will give you a very detailed help on the assignments, okay? All right, so then comes the midterm. The midterm is going to be about 20%, okay? Now, the thing is that we are not sure what format the midterm is going to be, because, we may or may not have offline midterm, that is in-person midterm. But if it is online, the way I like my midterm is that it's an open book. It's an open book exam. And I discourage students from Googling the, the problems, because if you Google the problem and you come across something very, very like similar on the net, and you just copy that, it's actually very easy for me to kind of, see that you are indulging in what is known as plagiarism, okay? And that is not allowed according to the honor code. So, so don't do that, but you're welcome to use books, that are assigned to the course. You're welcome to use the lecture notes. Just don't talk to each other, okay? And what I do is that the midterm will be, you will be given 4 to 5 problems, and you will have to do 3 problems. And I will give you 24 hours to do those problems, okay? So the way I do it is that one of the problem will be an easy problem that almost everyone can do. The other 4 problems will be medium to hard problems, so that students who are really paying attention, students who are really engaged, can make a difference, okay? And these are problems I make up myself. And so, or, I find them in some obscure book. So it's in your interest to actually think about it yourself than trying to, scour the internet to find the solution to these problems, okay? And you will have one day, right? So time is not going to be an issue. And I usually make sure that the exam is done on a day. Often it's on the weekend, and I'm sorry for that, but it's done on a day where it doesn't coincide with any other exam, so that you can approach the problems in a relaxed manner, right? Physics is about being relaxed and thinking in a relaxed fashion about the natural world. You should not be stressed about it. So I try my best to make sure that that happens, okay? And number 7 is 20% will be carried in the final or the equivalent assessment, okay? Sometimes what I will do is that I will throw in a graded quiz with the final or the midterm, or both. And what will happen is that graded quiz will be contributing to this 15%, okay? So, and yeah, the final will have exactly the same policy as the midterm. It's an open book exam, okay? And this is basically the grading policies. Do we have any questions?
No, sir.
Anyone
No,
else?
No.
Okay. Well, if you have more questions later, you can always you can always ping me. All right. So let's discuss some class policies. Okay, this is very important. Okay. So as I've already said, there is a policy about collaboration, highly encouraged, copying, highly discouraged, okay? And if you do copy, if I find evidence of copying, you will be reported to the proctor's office. And the proctor's office has a reputation of dealing with these things in a heavy-handed manner, unfortunately, but there's nothing I can do about that. Okay. The other thing is that this is a no sexual harassment zone. Just 1 second, okay? I think my cat wants to come in. Sorry about that. Yeah, my cat wanted to come in. Okay, so this is a no sexual harassment zone. I feel like life should be a no sexual harassment zone. And so I want to remind you that Bragg University is a safe place, and I take this extremely seriously, okay? Anyone who is found engaging in sexual harassment will be severely penalized, and they will face expulsion from this course. And depending on the severity of the, act, I may even disbar you from taking any of my future courses. Okay. So if, on the other hand, if you think that you are being sexually harassed, please contact me as soon as possible. If you don't feel safe contacting me, contact the proctor's office. As much as possible, strict confidentiality will be maintained. Okay. So I've heard a lot of stories at Bragg where, students will be working in groups, and then some male student will then start messaging some female student, sending them messages, even when the female student made it clear that she is not interested in such advances, the male student would persist. That is not allowed. That is not acceptable. Okay. So this is, I take a very strong position on this. Okay. So this is number one. Number two is that bullying. Okay. I also do not want there to be any bullying, and no bullying will be tolerated. You guys are now adults, so you probably know that schoolyard bullying is not the kind of stuff that you do anymore. But you'll be amazed that how many of my undergraduate students have told me that, sir, I have been bullied. A lot of times it happens when the student is doing something which is perceived as not, I don't know. For example, somebody asks you for a solution and you don't provide them with the solution. So put pressure on you. Sometimes they will use the dominant culture to kind of, give them the solution, and they may resort to bullying for doing things like that. So if you believe that you're being bullied, please contact me as soon as possible. The sooner you contact me, the better. The flip side of this is that I've seen many, many students bullying their teachers at Bragg. This is also unacceptable, okay? Every semester, especially in the large courses where there are 500, 600 students, there is a tendency for students to pressure the instructors to to pass policies which will maximize their grades, which will allow for longer time intervals so that they can go on various Discord groups and, and cheat and, buy solutions. We are aware of a lot of these things. So, in those cases, I've seen that when teachers are strict, when they say, no, we are going to have very strict, windows for exams because, you guys have not shown that you can be trusted, students sometimes resort to bullying. For example, a student was posting poop emoji to everything that their teacher, said. So these are examples of harassment and bullying, okay, from the students to the teachers. So if you have a problem with me and you feel not safe discussing it with me, you can always, email the academic complaints, hotline, or you can even approach the dean, okay, who is my superior. And, a lot of times, a friendly chat, a mediation is, will solve things. Okay, so that is basically what I have to say in terms of class policies. I may have missed something. Do you guys have any questions or comments? Please, you're welcome to speak out, okay?
Sir, I was hoping that can the class time be shifted to a little earlier, like in the morning or something?
Mornings are very difficult for me. I usually don't go to bed before 3 o'clock and don't get up before 11, sometimes even 1 o'clock. But we can. What's your issue? What's the problem you have?
Usually, sir, at this time I teach my students, so it's actually a class. So maybe 1 or 2 would be good. But if it's not possible, then I will defer my students. So that's all.
So, Erike, is this a private coaching thing or something like that?
Yeah, yes, sir. I teach.
Okay.
I have my students.
Okay. Yeah, maybe you should try to do that because we don't want to inconvenience everyone. Because I want to actually. Usually, I change the class time every semester, but this semester I'm actually mindful of trying not to change the class time because otherwise some students will be inconvenienced, right? Because it'll clash with some other. So I wanted to keep this slot. So see if you can do it. If you can't do it, then you are always welcome to watch the lectures later, and I will give you a waiver about attending the class. Okay.
Okay, sir. Thank you, sir.
But about the waiver, I must warn you that usually it takes me a day or two before I get around to posting the lecture. Okay, so you'll be a little bit in a time. There'll be a phase difference between the class. It usually doesn't affect very big in a major, but so see if we can have a compromise. Okay.
Okay.
Okay. Anyone else?
No, sir.
All right. Okay. My cat is trying to get on the computer. He wants to be badly part of the class. Okay. So I also want to discuss the timing for the tutorial. Okay. Sorry about that. Let me go back to this. Okay, so I want to discuss the timing of the tutorials, okay? So usually what I do is that I have the tutorial class on Saturday. So I'm going to propose that maybe Saturday 3:30 could be a good time. If that doesn't work, maybe the other option would be a Thursday 3:30 slot. But I understand that some of you might have classes on Thursday 3:30. Can we have, like, can people tell me?
Saturday sounds good.
Okay,
Yes,
Saturday
that sounds
3:30.
good.
Yeah.
I go for Saturday.
Okay.
Saturday is good with me.
Okay. Okay, Saturday 3:30. Okay, so I still haven't recruited the person who will be teaching the tutorial class, but I will do it this week, and hopefully by next week we can start the tutorial. So, usually the tutorial class is about 1.5 hours, but I actually encourage you to work longer until you have solved the problem. So I will try to recruit someone who will not be very stingy with their time. Okay. Another thing about the tutorial is that you don't always have to finish 100% of the tutorial. About 80% of the tutorial, if you finish it, should be actually good. The rest you can do it on your own. And then you will be asked there'll be a roster of people. You will be asked to write the solution collaboratively in a nice, way, and then post it. And after I've checked the solution, it'll be posted officially on Slack and uploaded onto the UX page. Okay. So is it decided that it'll be Saturday 3:30?
Okay, sir.
Okay. So what I will do today after class is that I will make a Google calendar, for this course, the Google Calendar, schedule, and I will share it with you. And I think if you accept invitation through your G Suite account, then in future classes, you don't have to ask for permission to come in. You can just come in, automatically, okay? So the tutorial, again, let me just remind you, your attendance is required at least 80% of the time, okay? So attendance. Because I think that the physics is really learned in solving problems, and the tutorial is basically a regular way of ensuring that you solve problems, okay? Okay, any questions?
No, sir.
Okay, the last thing I want to discuss is something slightly different. It's about mental health. Okay, so the pandemic has put a lot of pressure on us in terms of our family life, in terms of our mental health, right? Many of the students I know, their parents have lost jobs, lost way of income. That has put pressures on the how much they can support their kids. So, and as well as for example, many of you actually support yourself by doing by teaching. For example, Jabbar just said that he has to teach students, right? So many of my students are doing that. So all I'm trying to say is that it's not very easy to be able. It's not always easy to be able to navigate the pressures of the modern world. And what I would want ideally is that I would want this course to be something that does not cause you mental health issues, but causes you joy. Okay, but of course that's not always going to be the case, because whenever you challenge yourself in life, stress is an integral part of it. Now, the whole point of stress is that you want to be able to manage the stress, okay? So there is stress which is manageable and stress which is not manageable. When stress becomes too unmanageable, that's really what leads to, breakdown in mental health. And just like physical bodies, each of us have different mental makeup. So, someone might find taking might find it very easy to take on a lot of, commitments and pressures, but someone else might find it very hard to take on the same amount of, commitments. The point is that you should never compare yourself with others. We are all unique. If there's some kind of Buddhist saying that you cannot really be somebody else because that place is already taken, right? So you should always celebrate the person that you are. You should So if you're having, and I'm extremely sympathetic and understanding of mental health challenges that students go through, and and what kind of, and I try to accommodate those things, okay? And as long as it's genuine. So if you're facing challenges, suppose you're having problem concentrating, don't feel ashamed, don't feel judged. Please contact me. The sooner you contact me, the more help I can provide you, the more support I can provide you. Unfortunately, in Bangladeshi culture, as well as Bangladeshi society, mental health is a taboo subject, and I just want to change that. I want to change that, and I want to change that by admitting that I myself have suffered severe mental health challenges in my life. I've had nervous breakdowns. I suffer from anxiety. I take an antidepressant. If the anxiety gets extremely bad, I have emergency medication for that. I do regular meditation. I've been doing meditation for 5 or 6 years, and that has helped me immensely. And I have overcome to a large extent the stigma that is attached to mental health challenges. Okay, and I found that by overcoming, by not attaching shame or letting go of that shame and stuff like that, I am much more relaxed, and I'm much more happy, and I'm much more engaged. Okay, so this is something I want to encourage you. There are lots of free resources for meditation these days. A lot of resources for YouTube. Free apps. Lots of stuff like that. So if you are interested, you can always reach out to me in a private message, and I will try to help you in any way. And if you are facing pressure, family pressure, financial pressure and stuff like that, please reach out to me, and I will do my best to provide you with support. Okay. Okay. Any comment or questions?
I would just like to add that alongside meditation, if it's possible, it's better to just go out for a walk. Like, I know it's the
Exactly.
pandemic, but going out for walks has helped me tremendously, and I feel much better through
That's
meditation
very
and
good. Yeah.
exercise and going out. Yeah.
Yeah. Well, actually, going out for walks in the open space, that is actually good for your health, because you're not, there's enough air that the virus will get diluted. Just don't go out for walks in Jamuna Future Park, right? Without a mask. Go out where there's fresh air, right? It's hard to find in Dhaka, but I think I agree with Sujosh 100%. Or a bicycle ride, whatever works for you, right? Okay. Anyone else wants to chip in? Thank you very much, Sujosh, for that suggestion. Or you can play video games, right? Some people play video games, so, some people do yoga, so. All right, so, okay, so, this is, I don't want to close this topic because this is an ongoing discussion. And please, if you have any issues, reach out to me, okay? Okay, any more questions in general about anything?
No, sir.
Okay, in that case, let us move on and discuss something about quantum mechanics. And let me just give you the outline of the kind of stuff that I want to cover in terms of course content in this course, okay? So, although this is becoming less and less popular, I actually think that it's always a good idea to ask the question, why, do we need quantum mechanics, okay? Quantum mechanics is extremely weird. It's, I would say it's weird is beautiful in a weird way. Okay, and but very few people could have come up with the structure of quantum mechanics. So we will start with some semi-historical comments about quantum mechanics. Okay, so some history. It won't be. We are not interested in teaching historical quantum mechanics, but a little bit of history is going to be, in my opinion, helpful. So, but the topic of this course is non-relativistic quantum mechanics. So, the main topic is non-relativistic quantum mechanics. The interesting, you might say, why not relativistic quantum mechanics? And that would be a very good question. The relativistic quantum mechanics should follow from this, but actually there's a deeper reason. It turns out that when you try to marry quantum mechanics with relativity, quantum mechanics doesn't stay the same. It actually naturally leads to a new subject, which is called quantum field theory. And that is why usually in courses, in universities, you see courses on non-relativistic quantum mechanics and then quantum field theory. Okay? So the basic equation for non-relativistic quantum mechanics is the Schrodinger equation. The Schrodinger equation. So we shall discuss the Schrodinger equation in detail. Okay, so there is a parallel formulation of quantum mechanics, which is not in terms of Schrodinger equation, but in terms of an operator algebra and its equation, and those equations are known as the Heisenberg equations. Okay. Now the Heisenberg equations and the Schrodinger, for some time after the these two different formulations of quantum mechanics were discovered, it was of course observed that they both predicted the same experimental values. So which is like weird because they seem to be completely different. So what happened was that it was then Dirac, Paul Adrian Maurice Dirac, who was able to show that the Schrodinger equation and the Heisenberg equations are actually equivalent. By doing that, what Dirac did is that he elucidated the underlying linear algebraic structure of quantum mechanics. So Dirac did very, very important work in that line. And I cannot but, note here that Dirac also came up with the first, with the first successful relativistic quantum mechanical equation. This equation was the equation for the electron, but the equation also predicted that there be an anti-electron. So Dirac actually, in trying to marry quantum mechanics with relativity, he actually predicted the existence of antiparticles. And why did I say successful here? Because before Dirac, there were many unsuccessful attempts in marrying quantum mechanics with relativity. And in fact, Schrodinger himself found an equation which is now known as the Klein-Gordon equation. And the Klein-Gordon equation is consistent with relativity, but unfortunately, it's not consistent with the probabilistic interpretation of quantum mechanics. And that's why it was abandoned, and then until Dirac discovered a different equation. The Klein-Gordon equation has a quantum field theory interpretation, but that's something that is beyond the scope of this lecture, okay? So we will be taking the route of mainly discussing quantum mechanics from the point of view of the Schrodinger equation, but I will tell you how the Schrodinger equation is related to the Heisenberg equation, okay? So we won't entirely ignore the Heisenberg equations. The Heisenberg equations become very, very useful when you study, say, quantum field theory, for example. So there's another interpretation. There are another way of looking at quantum mechanics, that's known as the path integral interpretation. And this is due to Feynman. Okay? Although he was inspired by Dirac. Okay? He was inspired by a cryptic comment in Dirac's book. And he wanted to understand that comment, and he ended up discovering a new way of formulating quantum mechanics. Unfortunately, our course will not cover the path integral interpretation. It'll be covered in either in quantum mechanics 2 or quantum mechanics 3, okay? But if any of you are interested in path integral, I highly encourage you to read the book by Feynman and Hibbs. Okay. Feynman, sorry, it's only one N, and Hibbs. They wrote a really nice book on the path integral formulation of quantum mechanics. So it's a textbook. It's an introductory textbook. You can always read that. All right. So after that, what we'll do is that. By the way, any questions? Please do interrupt. Okay. If you have any questions. So Schrodinger equation, the formulation of quantum mechanics in terms of Schrodinger equation is known as wave mechanics. Because as we shall see, the Schrodinger equation is a kind of wave equation. Okay. It's a wave equation. So you might say, how does a wave equation describe quantum mechanical particles? And that's a very good question. Well, the way it works is that to each quantum particle, in fact, each quantum system, you can associate a wave function. Say it's usually denoted by psi, but we'll use other symbols such as phi, etc. This is a wave function, and it's a mathematical object, which is a complex function. It's a complex function of time. Okay. And the Schrodinger equation describes how this wave function evolves in time. Okay? And what you will see is that according to the postulates of quantum mechanics, the wave function, if you take the wave function and you square it, so if you say do something like this, take the wave function and you square it, and This gives you the probability density. The probability density of finding the particle in some state. And that state could be, say, in a certain region of space, or that state could be the energy of the particle or the momentum of the particle. We will discuss those things in detail later. Okay, so today I'm just kind of warming up the whole thing. Today it's going to be somewhat non-technical. Okay, so do we have any questions, by the way? You guys have been suspiciously silent.
No questions, sir. At least so far.
All right. Okay. All right. So that is our next thing. So then what we will do is that we will basically apply this to some simple one-dimensional system, okay? So simple one-dimensional systems. So these are systems that we will solve very explicitly. But I will do a more general, like, analysis of the Schrodinger equation in 3D. And for this, we will need a lot of linear algebra. We will need, in fact, we will need Fourier analysis. And you will see that Fourier analysis is essentially an infinite dimensional version of linear algebra, okay? So when we're doing this, we will also introduce some, the postulates of quantum mechanics. So for example, some mathematical ideas such as a Hilbert space, Hermitian operators, stuff like that. Okay. Unfortunately, quantum mechanics is quite mathematical. Well, that's the way nature is. We physicists don't like learning mathematics unless they need it for some application. It turns out that quantum mechanics is quite mathematical, so you have to learn some mathematics, okay? So, for example, Dirac, as I said before, Dirac elucidated the linear algebraic structure of quantum mechanics, but Dirac was not big on proofs, okay? He was not an analyst. So the mathematical foundation of quantum mechanics was put on firm footing by someone else. Do you know the name of that person? His name was Johnny von Neumann. Johnny von Neumann was probably one of the greatest mathematicians of the 20th century. He also laid the foundation of the modern computer along with Alan Turing. He was a faculty at Princeton, and he wrote a very famous and influential book on quantum mechanics called the mathematical principles of quantum mechanics. I think that's what it's called, yeah. In which he talked about convergences, the existence of, states as mathematical, what does the wave function actually mean, issues that has to do with convergence and stuff like that, okay? So we won't go into these mathematical foundation, but I want you to be aware that there are a lot of mathematical niceties and subtleties in quantum mechanics, a lot of which was resolved by Johnny von Neumann, okay? Okay, so So we are going to do one-dimensional quantum mechanics, and then we are going to discuss a very, very important system, which is called the one-dimensional simple harmonic oscillator. Okay. The simple harmonic oscillator is kind of the foundation of most of quantum mechanical examples that we see out there. And the simple harmonic oscillator, it is so important that we will solve it in two different ways. So we will solve it in two different ways. One would be by solving Schrodinger's equation. Another way is going to be a very beautiful and elegant method introduced by Dirac, which uses the algebra of the operators, okay? And then I want to shift gears and I want to talk about, identical particles and quantum statistics. Okay. Now, quantum particles are identical, like two electrons are the same. So they're not like twins. So for example, if we have two twins, they may look identical, but they are different people. But if you have two electrons, and if you put them in a bag, then when we take those electrons out again, there is no way of telling which electron is which electron. Okay? So suppose that there is some box, black box, and there's an electron A, say, coming in, and an electron B coming in. And afterwards, suppose that, the electrons go out. There is no meaningful way in which you can say that this is, say, electron A and this is electron B. This doesn't work. If this has the fact that electron A and electron B are identical has consequence in terms of their statistics, meaning that you can actually predict there are predictions based on the fact that they are not identical. And it's not just electrons, which are, say, spin half particles, as you will see. It's also so there are different kinds of particles, okay? And depending on their spins, they will have different statistics. So I want to cover that as well. Okay? So they're fermions and they're bosons. There are two kinds of statistics in three dimensions, three spatial dimensions. There are fermions and there are bosons, okay? I should use small f, because fermions are named after Fermi, and they follow what is known as the Fermi-Dirac statistics. And bosons were discovered by Bose, and then Einstein did very important work on that. Einstein, based on the work that Bose had done, Einstein found a new state of matter, which is now known as a Bose-Einstein condensate. And this was, discovered experimentally, I think in the 80s or something. And, there's a Nobel Prize given on it. And if you were in my StatMech class, we actually covered the basics of Bose-Einstein condensation. But of course, we won't do that here, but I want to introduce you to the idea of quantum statistics. Okay. All right, so after that, the next topic is an optional topic. I will probably not be able to cover it because of time constraint, but I just want to mention it, is that, the analysis of the angular momentum algebra, okay? So angular momentum in and 3D systems, okay? So, the type of particles that we have, like fermions and bosons, they can take very, very specific angular momentum values. These are known as spin values, but it's also very specific to 3 dimensions, okay? If you were in 2 dimensions, particles actually can have a more general statistics, and that statistics is known as anyonic statistics. And you might say, okay, we don't live in a 2-dimensional world, so why do I care? You actually can find systems which are very thin, so that they're effectively 2-dimensionals, quantum systems. And in such systems, there are what are known as pseudoparticles, okay? Pseudoparticles, and these are kind of vortices. And they act like particles. So you can have associate, wave functions with them. If you look at very high energy, like if you look inside, you will see that there are some complicated bound state of, say, electrons and phonons. But above a certain length scale, they look like particles, and these are called pseudoparticles. And you can have an effective quantum mechanical description of those things. And it turns out that they can have more general statistics, and that's known as anyonic statistics. And there's a lot of very beautiful physics and mathematics related to anyonic statistics, which has to do with, say, knot theory, braiding, or braided algebra, stuff like that, okay? And right now, there's a lot of experimental, work that is being done. So it's a very rich field. Okay. But I'm not sure that if I can cover the 3-dimensional angular momentum, because I probably won't have time. And that's because the last 1/4 or the 1/3 of the course, what I want to do is that I want to introduce you to the basics of quantum information, okay? There's no reason for me not to introduce it in an introductory class. In fact, there is a textbook written by Ben Schumacher and Michael Westmoreland, which introduces quantum mechanics from the quantum information point of view, okay? So this will involve, what is a qubit, that is a quantum bit. Then, although the idea of a density matrix is applicable to many things, but the idea of a density matrix is especially useful in quantum information. And then we will discuss, the basics of quantum circuits. Okay, circuits, and maybe some simple algorithms, quantum algorithms, as well as, say, quantum algorithms. Yeah. We won't really be discussing physical realizations. That's a bit beyond this course, but this is what we want to end the course with. Okay. So any questions?
This is kind of in the realm of quantum computing, right?
Yes, that's why I'm calling this quantum information. Yeah. So this is, going to be a hot topic in the future, hopefully. So I want you guys to be, I want you to know the basics of it, okay? What are the basic fundamental ideas, and I think CSE used to have a quantum information class. I'm not sure what the status of that is anymore, because the person who taught it, Wasif, left for his PhD. But we can revive that. Does anyone know if CSE is still offering that course?
CSE is offering quantum computing this semester.
Okay, so that's the same, yeah. So there will be some overlap between quantum computing and quantum and what I'm saying here. Okay. And I also want to say, talk about teleportation. Okay, quantum teleportation. And yeah, this will be very basic, but this is the aim. Okay, any more questions or comments? So let's consider today's class lecture 0, and I won't get into the stuff. I won't get into the nitty-gritty today, but in the next class we will start by discussing the limits of classical physics and why we need quantum mechanics. Okay. Okay. Do you have any questions in general?
I do have a little bit of a silly question, but is there a difference between quantum mechanics and quantum physics? Because I hear people saying both of those terms.
No, there isn't. It's used interchangeably. So essentially, what we call quantum mechanics came from, Schrödinger called it wave mechanics. Okay. Mechanics because it deals with particles. Waves because the fundamental equation is a wave equation. So this was what Schrödinger called this. And but Heisenberg realized that he formulated quantum mechanics in terms of the observables like energy, momentum, stuff like that. And what he realized was that those observables did not commute. And his friend Pascual Jordan told him that, oh, yeah, those are described by something called matrices. So what Heisenberg called his version of quantum mechanics was called matrix mechanics. Okay? And the word quantum was introduced in 1901 by Max Planck. Okay? When he realized that when he came up with the formula that described the radiation of a black body that is at a certain temperature accurately, he had to postulate that the atoms which make up the hot black body, their energy state was given by an integer times a small constant times a frequency. And that constant h is called Planck's constant. Planck's constant. But so the energy of the oscillators that make up the atoms, he approximated the atoms by oscillators. And, the energy is then what? It's quantized, right? Because it comes in discrete values. So quantum means discrete. And quanta is a disc. So, and because of that, Planck called this this quantum, Planck's constant is also called I think the quantum of action. It's a fancy name. This has, by the way, Planck's constant h. Its dimension is that of angular momentum. Okay, and you might say, why angular momentum? And that's because it has the same dimension as a volume element of like a two-dimensional phase space. Okay, and the phase space has a two-dimensional phase space has the volume element. The dimension of that is actually has the dimension of angular momentum. Okay, so because of that, I think wave mechanics and matrix mechanics got merged into quantum mechanics. But more recently, people have been kind of looking at quantum mechanics and thinking of, like mechanics is kind of an old-fashioned term. So a lot of people use quantum physics instead. Okay, so quantum physics is usually thought of as a catch-all term for both quantum mechanics as well as quantum field theory, okay, as well as quantum gravity. So sometimes it's used equivalently to quantum mechanics. Sometimes it means all these things. So, this is just a very informal way of talking about quantum mechanics. In fact, at PSI, where I taught for 10 years, our introductory course on quantum mechanics was called quantum physics. It was not called quantum mechanics. In fact, that course had a very quantum information flavor because, PI is one of the world's leading centers. Well, Waterloo is a world leading center for quantum information. The IQC, Institute for Quantum Computing, is there, and that actually grew out. That was an outgrowth of the Perimeter Institute. Okay.
Sir, there is also quantum electrodynamics and quantum thermodynamics. Are they?
Yes. So these are, that's a very good question. And those are part of quantum physics. Yes, they're a little bit different from quantum mechanics, but they're applications of quantum mechanics to, so the first one, quantum electrodynamics, is an application of quantum field theory to electrodynamics, which was, pioneered by Feynman, Tomonaga, Schwinger, and Freeman Dyson. Although Freeman Dyson was not given the Nobel Prize for that, but Freeman Dyson had an equally important role to play there. So, so quantum electrodynamics, known as QED, is essentially the quantum field theory of electrodynamics. Okay, how, electrons interact with photons, right? That's electrodynamics. And the quantum thermodynamics is essentially the application of quantum mechanics to thermal physics, okay? Thermal physics and thermodynamics, okay? Dynamics. And there's also quantum statistical mechanics, right? Which is very similar. So the quantum statistical mechanics, because, as you know from statistical mechanics, the probability that a particle has energy E is given by the Boltzmann factor in the canonical ensemble, right? And sorry, in the canonical ensemble or the macrocanonical? Yeah, in the canonical ensemble. So, and this is becomes slightly changed depending on the statistics of the particle. If you have a boson or a fermion, so there are some subtleties to the statement, and so those are covered in quantum statistical mechanics. I think in my statistical mechanics course, I did do quite a bit of quantum statistical mechanics. I think, was that Mashikur who said that, this comment?
Sorry, sir.
Who was it who talked about quantum stat mech?
Sorry,
Was it Mushik? Oh,
I think it was
yes.
not me.
Okay, I don't think you were in my stat mech course, right?
No, sir. The only physics course that I did so far was Physics 202, which was last semester. So
Okay.
this is my second physics course into the minor.
Okay, so another thing that people ask me is that what are the prerequisite for this course? There isn't a lot, but having some but you must have mechanics at least, and having some electromagnetism is helpful, but it's not essential. So it'll be a sophisticated course, but it doesn't have a lot of prerequisite. Having some linear algebra is also very useful, but I find that the way that linear algebra is taught as an undergraduate level at BRAC is not very helpful for quantum mechanics, because the way linear algebra is taught in mathematics in this country, its emphasis is more on just learning some algorithms by heart, or memorizing algorithm rather than understanding the underlying mathematical ideas of vector spaces. In this course, we are going to be more emphasizing on the underlying ideas of a vector space and how that relates to quantum mechanics. So in some sense, I will be teaching you linear algebra from scratch, hopefully. Okay, any more questions or comments?
Sir, is there any specific book that we're gonna follow, or like?
Oh yeah, there will be several books. I will post those names. I didn't get the chance to post those names when I made the BUX page. I will update that page maybe tonight. So one of the books I really like is Skinner and Binney. It's a recent book, excellent book. I also like very much Shankar. I also like an old book which I learned quantum mechanics from, Paul and I think Kreisman or something like this. And these are there's an advanced book by Sakurai and somebody else. Sakurai died before he could publish it. This is something I will use from time to time, not really very. There's also a book by Taylor and French, an old book. And I find that the treatment of one-dimensional system is excellent in Taylor and French. So I will be using these books a lot, okay? And for quantum information, I haven't decided yet. I might be using a lot of the Westmoreland and Schumacher book, okay? And so this is for quantum information. There's another famous book by quantum information, but on quantum information, it's by Nielsen and Chuang. It's a bit mathematical, but it's also a good book. I learned quantum information from this book. So yeah, I will post more detail of this. There are a few more books which I also look at from time to time. I will also post those names, okay? So yeah, I'm not keeping anything secret from you, okay? You will have access to all the resources that I use.
Obviously, yeah.
Okay. One thing is that never use like Indian notebooks. Okay. When we were kids, when we were undergraduates, a lot of teachers would recommend. So India has this sort of culture of using notebooks, and they were the worst books to learn from. The basic people who studied those books essentially didn't learn any physics. Shankar is Indian, but of course Shankar is not writing an Indian notebook. He's a faculty at Yale. I'm not saying that Indian faculties are bad, but there is a culture in Bangladesh of using notebooks which were used in Indian, like pass course and those kind of exams. So never, always use good books.
Those are basically like information dumps, right? I think I've seen them before.
Yeah, exactly. They're information dumpsters, but they're not. They actually have wrong information all of times.
So will you be uploading? Sorry.
Yeah, I'll be uploading my lecture notes. Yes.
No, I was gonna ask that if will you be like uploading the title with the authors, or will you be uploading downloadable links of the books?
I will upload the title with the authors, because the downloadable links, I think you guys are smart enough to find for yourselves. And I'll be violating some copyright policy if I do that. Okay. I actually like personally, and I appreciate. I mean, when you go to say LibGen, and all these books will be available in LibGen. Okay. But I actually own most of these books myself because I love having physical books. But that's just me. I'm from an older generation, so. Okay. Yeah, I should have every one of these books. Okay, any more questions or comments?
Sir, I had another question.
Yeah.
Sir, it was regarding the tutorials. Like, basically, it's going to be like, is it going to be like a hands-on problem-solving session, like where you do it in groups with like a supervisor or something like that?
Yes.
And
so what I'll do is that there'll be a Discord like a server or something, and the person who is going to be running the tutorial, they will make like a different like rooms, or I don't know what you call them. I've never actually like used Discord myself, and but it's easy to make different rooms in Discord. It's not possible to do that in Google Meet, as far as I know. And you will be working in small groups of 3 or 4 or 5. And what will happen is that the supervisor or the TA or the ST, they will go from one room to another, and they will just observe and maybe help you, get along by asking you questions. So they're not going to provide you with the solution. They're going to help you find the solution. Okay.
So we'll be having a TA throughout this course, right?
I hope so. I haven't chosen the TA yet because it's going to be a tough choice. It's not going to be an easy course, so I have to choose a TA very, very carefully.